Hey, everybody. So we're going to look at what we call the chain rule today. This is a pretty awesome tool that we have. This deals with how do we take derivatives when we've combined functions by composing them, right? We've seen how to deal with combinations of functions when they're multiplied and divided, added and subtracted, but composing them is something pretty unique to functions. We want to know how to take derivatives when that happens. So let's start with a little bit of an intuitive example. We'll state the chain rule and prove it, and then do a couple of example derivatives with the chain rule. So imagine, for instance, that you are dropping a probe into the ocean. Okay, so we drop a probe that's going to travel down, and let's say its depth is given by d of t, where it's let's say its depth is in meters at time t in minutes, right? So after every at any time in minutes, this function will tell us the depth of our probe. Maybe we've programmed it to travel at a certain speed or something like that, right? And then we also might have knowledge, in fact, humans do have this knowledge, of the pressure given a certain depth, right? So depending on how deep you are in the ocean, you can get different pressure. So this is pressure in atmospheres at depth d, which it's the same d as above in meters. Okay. So let's just think about these two functions for a second. We could use these two functions to find out the pressure on our probe at time t in minutes, right? And I should have been very, very clear. Time starting at the moment we drop it and then proceeding forward, right? So 0 times 0, we're at the surface, and after that, depending on how this thing is moving downward, we get different depths, right? So the combination of these two functions would give us the pressure given a certain amount of time, right? If I told you, well, it's been traveling for 10 minutes, you could go to your d of t function and say d of t tells me it's at a depth of 100 meters, and then we take the 100 meters, put it into the pressure function, and we get the pressure coming out, right? That's composition of functions, right? We can write this as p of d of t, right? This is a new function. I'm just going to call it fancy p. It's a function of time that gives us pressure, right? So we've created a new function by combining the two of those. We input time, we output pressure, okay? So let's think about changes in our depth and our pressure. Suppose we know that at some moment, the depth is changing at, let's say, 5 meters per minute, right? So this is our change in depth relative to a change in time. So at this point in its journey, right, we don't know if it's traveling at the same speed the whole time, but at this point in its journey, for every minute that passes, it gains 5 meters of depth. And let's suppose at the same time, pressure changes at 0.1 atmospheres for every meter. Okay. This is approximately true. I don't know that much about the dynamics of the ocean, but I looked it up and there were some decimals and things, but I made it simple. So about 1/10 of an atmosphere every meter. Okay, let's just take that as true. Right, so every meter lower we go, every gain of meter of depth leads to a gain of 1/10 of an atmosphere of pressure, okay? So we might ask ourselves, how fast is the pressure changing per minute, right? So if we're getting 1 atmosphere of pressure for every, so 1 atmosphere per every meter, and we're getting 5 meters every minute, what does that mean? Well, if we want to know how many atmospheres per minute, you say, well, in each minute I'm getting 5 meters, and each of those meters is worth 1/10 of an atmosphere. That's 0.5 atmospheres, right? For every meter we get 1/10, we get 5 meters in the minute, so we get 0.5 of them, right? That's multiplication. All we did there was multiply these two numbers together, and we get, in this case, 0.5 over 1. Let's look at our units. Notice that we get the units of meters canceling out. And what we're left with is atmospheres per minute, which is exactly what we wanted, right? This tells us that how a change in time relates to a change in atmospheres, okay? Let's put this in the language of derivatives. This is the derivative. This thing at the end is the derivative of our fancy, our derivative function here, right? Our fancy pressure function. Let's go through each piece of this, right? An atmosphere per meter. This tells us how pressure changes as a function of depth, dp dd, right? So the smaller d and the upper d are two different things. This second part of our multiplication tells us how depth changes relative to time, right? In terms of derivatives, that's dd dt, right? These are the derivatives of these two original functions with respect to their inputs, right? What we ended up with is something that told us how pressure changed relative to time. So we end up with the derivative of the composite function, okay? So this is the essence of the chain rule, how the derivatives of composite functions work, right? And what we end up with is the multiplication of the two relevant rates of change, right? If you think about this composite function here, this is the rate of change of the outer function with respect to the inner function, right? Because that inner function is actually the input for the outer function. So it's still what a derivative is. How does the output relate to the input? The input just happens to be its own function. And then we multiply that by the rate of change of this inner function with respect to its input, its derivative. And the combination, the product of those two tells us how the outer function relates to the inner input, right? And I hope that this computation here makes that somewhat intuitive, okay? All right, let's do a proof of this, and then we'll do some examples. Well, let me state it more clearly first. Let's make a statement of the chain rule. There's a few little details we got to worry about, but they're usually not too bad in practice. So the chain rule, we're going to say, let's have f and g be functions. And for all x, in the domain of G, such that, so here's where we have to be a little careful, right? We're going to input something to G. I haven't shown the composition yet, but that's what's going to happen. And we want to make sure the output can be dealt with by F. So the way we'll write this is for all x in the domain of G, so we're starting with something that G can handle, for which G is differentiable, and f is differentiable at g of x. So we're looking at the values of x so that they're in the domain of g, and g is differentiable there, and f is differentiable at the output of those x, right? Because we're going to be taking a derivative of f at that output with this composition, okay? The derivative, so in this, we have all this, the derivative of the composite function, so I'm going to call this capital F. Capital F of x will be defined as the composition, right? F composed with g, F composition of g, which we know to be f of g of x. The derivative of this function, so the derivative of this capital F, right? That's whose derivative I want. Little f and g are how we define capital F, but I want the derivative of capital F. The derivative is given by f prime of x is equal to f prime of g of x times g prime of x. Okay, so what are we saying here? Let's look back at this thing we did earlier. We took two derivatives and multiplied them. The first derivative, dp/dd, was how does pressure change as our depth changes, right? That was how does the outer function change as the inner function changes, right? Because remember, our composition was p being composed with d. We put d inside of p. This first derivative is how does pressure change as depth changes. This derivative here is how does f change as g changes, not how does f change as x changes, how does little f change as g changes. Then the second derivative up here was how does, okay, that thing that we put inside of pressure, depth, how does it change as time changes, right? That's our second derivative in this product. That's what we have here. Now this is telling us how does g change as x changes, and we're multiplying those two together to get the thing that we started with, which is how does f, big F, change as x changes, right? Just like up here, we get how does pressure change as time changes via this product, okay? So this is our chain rule. We'll do an example in just a second. I'm just gonna give one other notation we often see. We could write this another way. If we let y equal f of u, where u is equal to g of x, right? So I'm just giving these functions other names. We can write now that dy dx is equal to dy du times du dx, right? This is more similar to what we did up above. We're taking the function g and putting it into f, and we've called it u when we do that. How does y change? That's our outer function. How does this change as we put in the input x? We take the product of how y changes relative to its input, which happens to be the function u, so we multiply by how u changes relative to its input x, and that product gives us the overall rate of change of y with respect to x, the outer function with respect to the original input, okay? So there is our chain rule. So how do we prove this? This is an okay proof. I think it has a little bit of intuition in it. We'll see. We don't have to be. We're not responsible to know how to do these completely yet, but hopefully it's a little bit enlightening to see the logic of them. So we're going to start with, let's just take all this. We're going to start with all this. Copy. Okay, so suppose we have functions f and g, We have x in the domain of g, for which g is differentiable and f is differentiable at g of x, right? So we're starting with all that. That's our givens, right? So we want to prove that we then have a derivative this way. So let's define sorry, my notes looked a little funny there, but I just realized it was bad handwriting. Let f of x equal big F equal f of g of x, right? Defining our composition function. And let's also define, I called it h is equal to g of x plus h minus g of x. And let's also note that this means g of x plus h is equal to g of x plus capital H. Okay. Now let's look at the derivative of f prime of x, and we'll see where this capital H comes in. F prime of x, and I'm just going to start with the definition of the derivative. The limit as h goes to 0 of capital F of x plus h minus f of x all over h. Well, we know that the definition of capital F is that this is f of g of x plus h minus f of g of x all over h. Okay, so what do we have here? There's a change in our composite function over the change in our input, right? But it's not quite, the changes aren't quite matching up right, okay? We don't quite have it looks very similar to the definition of the derivative except for this composition. So we need to do something to make, to match the kinds of changes we're looking at, right? This is a change in the original input, h. The input to f is changing by some kind of change in g, okay? That's where this h, capital H, comes in. I want to look at the change of g. I need to get that involved outside of this composition. So I'm going to multiply by 1. This is all happening inside the limit, but the way in which I'm going to multiply by 1 is capital H over capital H, or g of x plus h minus g of x all over g of x plus h minus g of x. Okay, now I'm just going to do a little rearranging. Limit as h goes to 0, so I've got some fractions here. I can rewrite these as f of g of x plus h minus f of g of x all over, so I want g of x plus h minus g of x times g of x plus h minus g of x all over h. Okay, so what you see is all I did was swap the denominators, right? And that's perfectly valid by the rules of fractions, right? If you don't see that, AB times CD, we could write this as AC times BD, which is the same as AC over DB, right? We can switch the order of multiplication, and then we get AD times CB by just rewriting that fraction. So we can swap numerators and denominators as long as we're swapping factors that way, okay? All right, now let's use this notation of h, and this is really just going to make things easier to see, I hope. So g of x, we have f of, I missed a parentheses here, f of g of x plus h. Notice that by this definition of h, this can be written g of x plus h, g of x plus h all in the parentheses can be written as g of x, and then outside the parentheses plus capital H. So we have f of g of x plus h minus We'll leave that one alone. F of g of x. All of this, and then the denominator, I'm just going to substitute in this original definition for capital H. Okay. All right, we're almost there. We're going to use one of our limit laws. I can split this limit up over a product. So I can rewrite this whole thing as the product of two limits. Okay. This second product, we recognize that's the definition of the derivative of g. And remember, we started with g being a differentiable function, or it's differentiable. We're looking at the x's for which it's differentiable. So we know that that derivative exists, right? Those are the only x's we're talking about. So here we have the derivative. I want to make a switch to this limit here. Here's maybe the most hand-wavy part. Let's look at capital H. Let's do this off to the side. So I'll remind us, capital H is equal to g of x plus h minus g of x. What happens, the limit as h, little h goes to 0 of capital H is the limit as little h goes to 0 of g of x, whoops, plus h minus g of x. Well, remember, g of x is a differentiable function, and that implies continuity. So the limit as we approach g of x as h goes to 0 is just going to be g of x. It's going to be the value there. When h is 0, we're just getting g of x. So we end up with g of x minus g of x, or 0. What this is showing me is that as little h gets smaller, so does big H. The way we've set them up, as little h goes to 0, big H is going to 0. And so I'm going to turn this limit, because it's equivalent, right? This is a little bit hand-wavy, but it works out, that I'm taking the limit as big H goes to 0. F of g of x plus h minus f of g of x all over big H. And remember, this piece we already said is g prime of x. Okay, now let's look carefully at what we have here. This g of x and this g of x are just the input to f. And we're taking the input plus some little bit that I'm calling capital H, subtracting the function at its input, g of x, and then dividing by that little bit, right? This is the definition of f. This is just the definition with respect to the input g of x. Okay, and that's where we find, remember, we insisted that f be differentiable at the outputs g of x. So the only x we care about are the ones where f of x is differentiable here. So these are those outputs where it's differentiable, and then this is just those inputs, right? We could think of these as something else like u or some, it doesn't matter the letter we give it, right? G of x is a perfectly good symbol, but it makes things maybe a little bit complicated. But this is just the definition of the derivative at the point, at the values g of x, and then we have our g prime of x, right? So this is our f prime of x. All right, maybe we can write it this way. This is a nice way to see it, just to make it very clear, except for how badly that g looks. The derivative, I'm not writing any new information here, just different notation, a lot of parentheses. The derivative of a composition of functions is the derivative of the outside with respect to the inside times the derivative of the inner function with respect to the input. Okay, maybe that was intuitive, maybe it wasn't. Let's do some concrete examples to help us understand how this works, right? Sometimes it takes a while for the ideas of these rules to set in. In the meantime, we can understand how to work with them. We can apply them. And I think sometimes that helps us get a better sense of why they work the way they do with some practice. So let's do a composition function. Let's take this derivative, d dx of the sine of x squared, right? So I've taken x squared, put it inside the sine function. So after a lot of practice, we might be able to do some of this very quickly, almost in our heads, but let's really organize here, okay? So I'm gonna do some work off to the side. I'm gonna write this function as a composition. So I'm gonna take f of x to be the sine of x and g of x to be x squared, okay? So then this derivative, right? Notice that means that f of g of x is sine of x, sine of x squared. All right, that's our function. So I'm just going to write that over here. This is f of g of x. I don't have to think for this next step. I have a definition. Definition of a derivative of composition of functions just looks like this: f prime of g of x times g prime of x. So let's compute some of these things. F prime of x, we learned in one of the earlier videos, the derivative of sine is cosine. G prime is 2x. Notice I have f prime of x here, but I want f prime of g of x. Well, that's easy enough. F prime of g of x means compose the derivative of f with the function g. In other words, compose cosine with the function x squared. And now I just write all these pieces down. F prime of g of x I got as cosine of x squared, and g prime of x is 2x. This is 100% correct. For whatever reason, I hate having that 2x at the end, so I'm going to rewrite it this way. This is purely an aesthetic concern. There's our derivative of this composition of functions. Okay. There's a lot of moving pieces here. There's no better way to get used to all this than writing out what I wrote out over here, right? Find a way to write this function as a composition. And then write the derivatives of all the pieces of your functions, and then put the pieces back in the right place, and you've got your derivative. Okay. All right, let's do one more example in this video. We'll get to some harder examples in some later videos, but I want to make one more point here. Let's suppose I give you the function y equals 1 over t squared plus 1. Okay, let's do a little split here. So we can actually do this already using the quotient rule, right? So let's see that. If I take f of x is equal to 1 and g of x is equal to t squared plus 1, then I can say that y is equal to f of x over g of x, which means that y prime is equal to f prime of x, g of x, minus g prime of x, f of x, all over g of x squared. Right? And I can come over here and compute f prime of x is 0, g prime of x is 2x. And if I put everything in the right place, so f prime is 0, so this first term goes away. I get a negative. G prime is 2x, f of x is 1, so there's nothing there. And then g of x squared means we've got t squared plus 1 squared. And there's our derivative. And that's perfectly acceptable. But notice, I can also rewrite this function this way. T squared plus 1 to the negative 1. Now I can think of it as a composition of functions. I could take Oh, sorry, I switched to X. I'm going to take the coward's way out. Instead of rewriting all of those things, I'm just going to rewrite this as an X. Let's do the same thing here. Sorry about that. Oh, I switched back and forth a couple times. That's awful. All right, I hope the point wasn't lost in all that mayhem. Okay, anyhow, we can write that f of x is equal to x to the -1, g of x, let me leave myself some space to take derivatives. G of x is equal to x squared plus 1. So then y can now be written as f of g of x. And again, without having to think, I can say, all right, well, here's the derivative of y. So I need some derivatives over here. F prime, we're gonna use our power rule, will be negative x to the -2. G prime of x will be 2x. Remember, I want f prime of g of x, not f prime of x. So I'm just gonna take this and compose it with g. So I'm gonna get negative x squared plus 1 to the -2. Let's write out, let's put all the pieces in place. I've got f prime of g of x, I've got sitting right here. So I've got negative x squared plus 1 to the -2 times g prime of x, which is 2 of x, right? And depending on how good you are at seeing exponents and things, they don't look exactly the same, but these are precisely the same thing because this x squared plus 1 to the -2 simply means 1 over x squared plus 1 squared times 2x. And then, of course, we can just write this as -2x over x squared plus 1 squared. And there's our y prime, right? Both of these are acceptable, and you'll develop some opinions about which one is easier for you to do, right? I tend to use the chain rule over the quotient rule. I think in this particular example, it worked out so that the quotient rule was easier, probably because of the 0 here. But I often find the chain rule to be a bit easier once you're used to it. But that's not a hard and fast rule, and that again is mostly a style choice. They're both completely appropriate. The most important fact is that if you can write it as a quotient accurately, if you can show me what is the numerator function and the denominator function, and it definitely represents your function, then you are free to use the quotient rule. And if you can write it as a composition accurately, so you have the right functions that when composed give the given function, then you can use the chain rule. If you can do both of them, then you can choose. And sometimes you can do that. You might be able to write it as a product rule, right? For instance, this function we have now could be written as a chain, if we wanted to take a second derivative, I won't do it in this video. This is a quotient rule as it's written here, maybe a quotient rule with a chain rule in the bottom. But I could also write it the way it was written just a moment ago over here, and then use the product rule with a chain rule in it, right? So there's often lots of different ways that we can approach these things, and as long as what you decide is correct, meaning I use the quotient rule because I do have a quotient, or I use the chain rule because I do have a composition. Okay, that's it for this one. We'll do some more examples, right? One big question you might be asking yourself is, what happens if we nest more than 2 functions? We can compose more than just one function with another. So we'll look at that and some more complicated iterations of all of this. But that's for next time. Thanks, everybody. I will see you then.